how to design an in situ humus tank or preliminary settlement tank or final settlement tank. These type of structures are actually present in water recycling process. All right, so here is a simple preliminary settlement tank with a diameter of around 14 meters, to be exact 13.6 meters. The height is 2 meters. As you can see, this circular area at the center, we called it hopper, has a height of 1 meter and a diameter of 2 meters. The base has a slope of around 7.5 degrees. Normally, this is 1 to 2% to allow the sludge to go on the hopper area. All right, so let's get started with the modeling. So what you can see right now are the axes. I've already established my axis. It depends on the dimensions or the general arrangements of the structure that you're designing. So as you can see on the screen, I have all the grid lines. Basically, this will facilitate me to model the cross-section of half of the cross-section of the preliminary settlement tank. I will use this polyline over here, and I will go to this polyline option here for the definition method. I will start from the center, and then I will go somewhere on this area. I will move up, then I will go on that area. I will extend a bit, and then I will hit apply, and then I will make another polyline on this one for the wall. All right, so what you see on the screen is a half cross-section of the preliminary settlement tank. Now, to be able to draw complete geometry, all you have to do is select all these polylines, and you go to geometry, and then from here you select these options on the objects, and then there's this option revolve. On this area, you have to specify the axis beginning, which is any point on the center of revolution. Let's say we will choose the base, and then you choose another point somewhere on the vertical, and then you specify how much or what degrees is the revolution. To have a one complete revolution, you have to specify 360 degrees. All right, and then here, as you can see, this number actually denotes how many segments or what's the mesh that you're going to provide for your element. For me, for example, for this type of structure, the diameter is 13.6. I will have approximately 1 meter mesh. So what I have to do, I will multiply 3.1416 pi multiplied by the diameter of this structure, which is 13.6. So that's around 43. So I'll specify here 43. And then hit apply. There will be a warning, but you just have to ignore it. Boom. So here is the geometry of our preliminary settlement tank. Now, before we proceed, let's have first our assumptions for this design. All right. For this, we will be using Eurocode, basically BSEN, if you're familiar, I hope you're familiar, 1991-1-1-2004 with National Annex of 2005. And of course, we will be dealing with the ultimate limit state design for the check of elements, basically providing reinforcement, and definitely SLS for settlement and deformation checks. Now, for this presentation, we will not complicate it, so we will be omitting crack width check. That's coming from your flexural crack width, basically the quasi-permanent loadings, blah blah blah, and of course following the provision of Syria. So we will do a separate video for that. For this, we will be assuming a maximum settlement of around 50 mil. That's for water retaining structures. We will do a bit check of the differential settlement, but I think this is not so much critical for this type of structure. And for the soil bearing capacity, we will be assuming a 75 kilopascal maximum, but this data should be given to you by the geotechnical engineer, or you should see this one from the geotechnical report. For the material properties, we will be assuming an F prime C of 3545 megapascal. All right. And for the thickness of elements, let's have, okay, for the initial sizing, for the thickness of wall, I will be assuming a 350 mil thickness of wall. But in case you don't have any idea how did you come up with 350 mil, it's basically the height of water multiplied by 0.2. That is to consider water tightness. That's usually the rule of thumbs that I am using. Or it can also be the span divided by 40. Okay, let's just forget about that one. We'll have separate discussion how to do initial sizing for structural elements later on. And for the thickness of slab, I usually do a quick check of the total pressure multiplied by 10. For this case, I will be assuming 350 mil, right? Thickness of the base. So in other words, the thickness of the wall and the thickness of the base is the same as 350 mil. Now here's the tricky part, the soil or geotechnical input. All of the geotechnical input should come from the geotechnical engineer. There should be a soil report on that. But in case there is no soil report or something like that, we need an input for the KZ. I do have an approximation, but usually it's just an approximation, all right? If you don't have the KZ, but you have the maximum soil bearing capacity of 75 kilopascal, for example, I usually use the formula. It's not a formula. It's just most of the engineers are actually using it. It's actually 120 multiplied by the soil bearing capacity. All right. So for example, your soil bearing capacity is let's just have 50, for example, soil bearing capacity, but we do have 75 there. For realistic calculations, let's just say 55, for example. This Q is 55. 120 times 55, that's around 6,600, approximately 7,000 kilonewton per cubic meter. All right, that's my assumption for the K sub Z. But again, these should come from the geotechnical engineer. Now, these K sub Z, or the soil or subgrade modulus, should come from the geotechnical engineer, and usually they derive it using Bohl's theory, plate load test, or adjusted using elastic theory. This is more realistic, and I think this is more this is near to the adjusted using elastic theory. You can do some research about that, but definitely I wouldn't suggest Bohl's formula because it will give you a unrealistic value for your settlement, but it's actually good for the distribution of loads. But I suggest you should use the value of K sub Z that's coming from the geotechnical engineer. All right.